Greetings, students of this institution, Mindanao State University. This video lecture is for you who enrolled in this course, Math 049 Pre-Calculus. My name is Archie Gambota Durig, a GTA graduate teaching assistant of Faculty of Mathematics Department at the College of Natural Sciences and Mathematics in this university. I'm your video lecturer of the topic Relation, Function, and Algebra of Functions. So set back, ready your notes, because we'll start in a moment. Definition 3.1. A relation R between two sets A and B is any subset of the Cartesian product A cross B. The domain of R denoted by D sub R is the set of all A in A such that the ordered pair AB is element in R. The image of R denoted by I R is the set of all such that the ordered pair AB is element in R. Now, if the domain of R is equal to the set A, then R is a relation from A to B. Then the set B is called the range of R. Example, let A be the set elements 1, 2, 3, and B be the set with the element AB. Then the Cartesian product of A and B denoted by A cross B is this one. So we have 1A, 1B, we have 2A, 2B, and lastly 3A and 3B. Given the relation R sub 1 with this element and R sub 2, take note that R sub 1 is a subset of A cross B, or the Cartesian product of A and B. And also with R sub 2 is also a subset of the Cartesian product A cross B. Then R sub 1 is a relation from A to B. Since the domain of R sub 1 is 1, 2, 3, so we can verify this is the domain of R sub 1. We have 1, 2, and 3. Because the domain is the set of all element in the first set or in A, which is equal to A. So if the domain of the relation is equal to A, then that is a relation from A to B. Then the image of R sub 1 denoted by I of R sub 1 equals the set with elements A, B. This is the image now of R sub 1. And R sub 2 is a relation between A and B where the domain of R sub 2 equals to the set 1, 2. So this is the domain, the element of the domain 1 and 2. And the image of R sub 2 is just the element B. So this is the image B and another. The figure below shows that the relation R sub 1 mapping from A to B. So we have this illustration. We have the set A and B with its corresponding elements. Our A is 1, 2, 3, and our B is AB. So the first element here is 1 mapped to A. So we have 1 mapped to A, and the second is 2 mapped to B. So 2B, and lastly 3A. So 3 mapped to A. So this is an illustration of this relation R sub 1. Another example, consider the relation S of the set of ordered pair xy such that x squared plus y squared equals 4. Some elements of the relation are given in the table below on its graph. So this is the table of values of this relation above. And plotting this table of values in the xy plane. And we can see that the graph here, the domain of the relation S is the set of all x in real numbers such that x is between -2
and positive 2 because x here lies in the x-axis and x is element of real numbers. And the image of s in the x-axis lies in this axis. So we have y, element of real numbers such that y is in between negative 2 and positive 2. That is the domain of S and the image of S. Another definition, function f from A to B denoted by f such that A mapping to B is a relation in which each element x in A is paired with exactly one element, and that is denoted by f of x in B. In this case, A is the domain of f, denoted by df or d sub f, and B is called the range of f, denoted by r sub f. Symbol read as f of x and called the value of f at x or the image of x under f. Example 3.5. Okay, in previous example 3.2, we have the relation r sub y, and it is a function because according to the definition of function that all element in A must be paired with exactly one element, and we have here all the element of A, which is 1, 2, and 3. And the relation R sub 2 of this set 1b and 2a is not a function because there is an element here in A that is not paired in this relation, and that is 3. So R sub 2 is not a function. In example 3.3, the relation S is not a function because the ordered pairs we have shown in the table of values, we have negative square root of 2 and positive square root of 2 and negative square root of 2 and negative square root of 2. They have the same first component. So that is why this relation S is not a function. Another example, consider the relation G with the elements of the ordered pair xy such that x equals y squared minus 4, whose graph is shown below. And the element, notice that the ordered pair negative 3, 1, 3, negative 1 are elements of G. So we have negative 3, positive 1, and negative 3, negative 1. So these are the elements of G which has the same first components. So we can say that the relation G is not a function. And this can be justified further by a vertical line test if the graph intersects the vertical line test more than once, and that is not a function. Another definition, let f and g be a functions from A to B. The functions f and g are said to be equal, denoted by f equals g, if f of x equals g of x for all x in A. Let us illustrate those further with this example. So let f, h, and g be functions from real number to real number defined by the following. So we have f of x equals the square root of the quantity x minus 1 squared, and h of x equals x minus 1, and g of x equals the absolute value of x minus 1. Note that f of x here, f of x equals g of x for all x in R. So we can have as f equals g. However, f of x at negative 3 equals 4, and h of negative 3 equals negative 4. Thus, f is not equal to h. Example, let f and h be functions defined by this. We will determine if the function f and h equal. So usually we do this by cancellation. So we cancel here x minus 1, then we can have f and h equal. But the domain of f is a real number except positive 1, while the domain of h is all real numbers. So we don't have f and h equal. In fact, h of 1 equals 3 here, and f of 1 is undefined. However, for all x in real numbers except positive 1, f of x and h of x is equal. Hence, we can stick the domain of h to real numbers except positive 1 so that we can have f and h equal. Definition: let f and g be real valued function, and we define the sum f plus g, the difference f minus g, the product f times g, and the quotient f over g as following. So we have f plus g of x is just equal to f of x plus g of x, and f minus g of x is f of x minus g of x, and f times g of x is equal to f of x times g of x. And so with the quotient, we have f of x over g of x, provided that g of x should not be equal to 0. Because when this g of x will be equal to 0, then the quotient is undefined. So note that x must be chosen that both f of x and g of x are defined. So the domain of the sum and the difference and the product is just equal to the domain of f and the domain of g. And so with the domain of the quotient is just equal to the domain of f and the domain of g minus the value of x such that this g of x is equal to 0. So we exclude here the x that makes g of x equal to 0, for that our quotient will be defined. Example, given f of x equals 2 over x plus 1 and g of x equals 1 over x minus 1. So we're going to find f plus g, f minus g, f times g, and f over g. Determine the domain of each function. Since f is not defined at x equals negative 1, so when x here is negative 1, our f of x is not defined. And so with g is not defined at x equals 1. So at x equals 1, g is not defined. Therefore, the domain of f is the set of all real numbers except those value of x that makes f undefined. The value of x that makes f undefined is x equals negative 1, and the domain of g also is the set of all real numbers except positive 1. So this positive 1 here, it makes g of x undefined. So that is the domain of g and the domain of f. Thus, the domain of their sum, the quotient, and the product is equal to the domain of f and the domain of g. So it's just equal to the set of all real numbers except negative 1 and positive 1. Okay, moreover, the sum of the function. So f plus g of x is equal to f of x plus g of x, and this one here, the function f of x plus g of x. Then algebraically, so we are going to find the LCD here, and this is the LCD x plus 1 and x minus 1, and this is the sum. And also the difference f minus g of x is equal to f of x minus g of x equals, this is the f of x minus g of x. Then find the LCD, and this is the difference. Under product, we have f times g of x is equal to f of x times g of x. This is the f of x times g of x, and this is their product. Next is f over g of x just equal to f of x over g of x. So this is f of x, 2 over x plus 1, and yung g of x natin is reciprocate natin since g of x is 1 over x minus 1. The reciprocal is x minus 1 over 1. Then multiply 2 times x minus 1 and x plus 1 times 1. So we have this quotient. Note that the domain of their quotient is just equal to the domain of f and the domain of g. So this is the domain of f intersection the domain of g minus the set of all x such that g of x is 0. So when our g of x equal to 0, so this is just empty because there is no such value of x that makes g of x equals 0. So the domain of the quotient is just equal to the set of all real numbers except negative 1 and positive 1. Another example, let f of x equals the square root of x plus 3 and g of x equals x cubed. So we will find now 2f minus g plus 5 and f times g minus f plus g. So we have the solution here. 2f minus g plus 5 of x is equals to 2, and then f of x minus g of x, here our g, plus 5. So 2 times f of x, this is 2 times the square root of x plus 3. Then minus g of x, so this is our g of x, and plus 5. Then simplifying further, since no like terms to be simplified, and that is the final answer. Then f of x minus f plus g, then f times g minus f plus g of x is just equals to the product of f and g of x minus f of x plus g of x. So we have their product as this one here is the f of x and this is the g of x. Then minus f of x and we have g of x. Then combine like terms if no further terms to be combined, and that is the final answer. That would be all for this video lectures. So be updated students for more video lectures to be uploaded, and thank you for listening.